Let's start today's class. It is a series of 3 lectures on memory interface. So today in the part 1 we will start with address decoding. Okay. So we know already we saw how a RAM look like. We have seen the internal architecture of a RAM also. So a RAM will require a few address lines. So 2 to the power of n, there will be different rows available in a RAM, right? So that means 2 to the power of n different memories are available. So each memory could be a few, it could be 1 byte or 2 byte or 3 byte. So that depends on what kind of RAM you select. So accordingly the number of data lines will change. If it is a single byte memory, then there will be 8 data lines, and if it's an 16 bit memory, then there will be 16 data lines accordingly. Also the RAM requires the chip select input, wherein through which we select the RAM. Okay, the entire thing will be known as an RAM chip. So that can be selected. So most of these signals are active low. So chip select will be an active low signal to select this RAM. And then we also have 2 control signals, which is known as an write enable. So whenever we want to write a data into the memory, to the write enable signal, since it's an active low signal, this has to go low. So when it goes low, so whatever is data available on the data line, that gets stored into the RAM. Okay, let me increase the size of the mouse a little bit. Whatever is the data available, that gets written onto the RAM. Similarly, when we want to read the data from a RAM, generally we don't directly connect the RAM cell onto the data lines, because the huge capacitances on these buses might corrupt the data which is already written in the RAM. So during read operation, we read it through a sense amplifier. Okay, whenever we do a read operation, so we need to give a low signal into the output enable pin of the chip. So that will in turn bring an sense amplifier into the circuit, so that the data doesn't get corrupted. It is amplified and then sent into the the cell is connected onto an data bus. Again, even here also, generally you will see it is connected through an bidirectional buffer. Okay, in between there will be a bidirectional buffer. Okay, so this is how a memory cell is organized. Now if you see various memory chips, there will be different specifications. Not necessarily a memory chip will have 1 MB or 500 KB memory space. The memory chips, they come with different capacities. So a 2K memory, for example, will have 11 address lines, because there are 2 to the power 2K different 2000 different 2000 is an approximate figure, right? And it is known as 2K, but it is not exactly 2K. It is close to 2000. So 2 to the power of 11. So that will I guess will come 2024 or something like that. Okay, but it is generally known as 2K. Okay, so that is so even 1K is I think 1024. And 2K will be double of that, 2048. So 1K to 1024 is generally known as 1K. Okay, so you have these address lines. So you for 2K memory chip you will have 11 address lines. Okay, and there will be 2 to the power of 2K different rows, and in each of the rows there will be 8 unique memory cells, so that the data they will all be that data will be taken in a parallel, so that you have D0 to D7. So you will have a 1 byte data line which will be connected onto this memory cell, and then you will have a read bar signal, a write bar signal, and chip select signal. Okay, So when we say 2K memory chip, we specify 2K into 8. Okay, that means there are 2K different memory locations, and each memory location is an 8-bit memory location, right? So this is how we specify a memory chip. Right now, how to no, so not necessarily we connect every time 500 KB cell to the 8086, or therefore a small requirement that suppose we want to just connect a 2K into 8 memory chip. So what is the hardware which we are going to do, right? So one option available with us is to earmark all these address bars as 1. So for 2K you require just 11 bits, right? So the address bus needs to be only 11 lines. So you can start from 0000 and end at 1111 here. So this will give you give us as 2K unique addresses. Okay, so and you can put all ones out here, right? If you put all ones out here, so this is what you need to decide. You can put all zeros also. So suppose in this particular example, we have considered let's consider this all as ones. So these are the address lines which we are going to use in the in our program, in our software, because we are going to put. So this is the starting address and this will be the end address of the memory. So in the hardware, what we need to do is we need to give A0 to A10, which are the 11 lines as the address bit, and then since we are going to put all ones out here, so we have an NAND gate, because this is active low, this is CS bar, chip select bar. So we are going to put a NAND gate and select this chip. So this is how, if at all we want to connect only one 2K into 8 memory into 8086. So this is how we are going to connect it. And in the program we are going to use from FF800 to FFFFF. This is the memories which we are going to use. Okay, is it clear to all of you? Okay.
So FF800 is the starting address and FFFFF is the ending address. Is that right?
That is the ending address. Okay. So
and that depends on whichever chip is being manufactured. Is that right, sir?
It depends, because we are going to use say for a particular application. Okay, we are making only a small program, we are making using 8086 for some small program. So we don't have to use always the biggest for 2 MB or 512 into 2 RAMs always, right? So so we can probably use 2K into 8 and finish it off with that also, right? Depends on the, say for any specific purpose, we just have to use 8086 to read something, for automating, say, washing machine or something. You don't require the entire and so much of big memory for that. So we are going to use a small memory, for smallest available memory. So probably we'll select a small memory chip and accordingly modify this hardware. Is it okay?
Yes, sir.
Okay. So this is an example. If we want to use all zeros out here, so accordingly in the software the range of the memory will be from 0000 to 007FF. So this range would change here. Again the inputs will be from 0 to 8 to the power of to A0 to A10, that is the 11 lines which are required to select the 2 to the power of k rows out here in the memory, and then you put an OR gate out here, right, to the chip select. So if all are zeros out here, only then the chip select. If there is any one here, this will not get selected. So this is how we implement. This is another option of implementing the same thing, connecting an 2K memory into 8086. Okay. So let's come to one more slide. Okay. So this known as address decoding, what I just explained to you. So right now we discussed how to do it with logic gates. we can also do this decoding using decoders. Okay. And then you can also do it with PLAs, PLDs and FPGAs. Okay. So we saw this is what, this is only implementing an logic circuit, right? And this we learnt in our digital class, how to implement these logic circuits with gates or with decoders, right? We did implementing of a function with decoders also, right? And with PLAs also. So whatever we learned, we are going to use that now here, right? Okay. So this is another example of doing it with the gates. Okay. Now here design an address decoder for a 32K into 8 RAM. Now 32K. Okay, now how to remember these things are a pretty easy. Number of lines which are required for 32K and all is pretty easy to remember. If you see 10 stands for 1K line. Okay, always remember, and 10 is, you can relate that, you can remember that 10 lines stands for 1K. So 2K is 11 lines because it keeps going in multiples of 2. And 12 stands for 4K, and 13 stands for 16K, and 14 stands for 10 for 1K. So obviously 2K will be 11, and 4K will be 12. 13 will be 16K, and 14 will be 32K. So that those kind of, so it goes on like that. So you can remember it that way. So now for 13K you require these many, 15 lines you require for 32K, 15 lines out here. So these are the 15 lines. So the starting will be all 0 0 0 here, and this will be all 1 1 here. So in this case, in this particular example, either I told all of them can be put as zeros or 1, or you can not necessarily zeros or 1. You can put any value for that, any unique value you can put here. Accordingly, the gate needs to be designed. That's also here it is all 0 0. So you put an OR gate, and then we give it to the chip select here, right? So it starts from 0 0 0 0 here and ends at this value, right? So this is how for a 32K we do an example. Okay.
So we have to ensure that we give 0 to a chip select bar. Is that right? Based on the combination.
Yeah, based on the combination. Yeah. So, and in the software, since we have put an hardware like this, in the software we'll have to restrict using this range of memories. Right? When you write a program, accordingly we have to restrict ourselves, and we should know, okay, what are these bits, and in hardware, and since it has been hardwired like this, so we have to be careful with writing our program. We got to restrict our range within this. Okay, if you write something else out here, okay, in your software, then it will go nowhere because there is no chip connected there. Okay.
And we do the restriction using masking, sir.
No, this is like not masking. This is a memory address, right? So we just have to know that, okay, our memory starts from here to here. Okay.
Yes, sir.
When we write a program, we just have to keep in back of our mind, okay, this is the memory which is available to me. That's all. Okay. So this is another example where design an address decoder for 8K RAM from this value. Okay, now the software engineer has decided he wants an 8K RAM starting from this address, and 8K ROM starting from this address. Okay, so he has already decided. So now we need to implement the hardware accordingly. So if you see 1E00, okay, so this is the equivalent binary for 1E00, and from there 8K. Okay, you need to add another for 8K you have 12 lines which are required. So these are all ones which are 0000 here, and for 8K 8K stands for 12 bits. So all 1111 has been put here, right? And he has, this is also fixed because he has started from this memory location. So this is the starting address, and this is the last address of the RAM. and for the ROM also he has given the starting address to be FA000. So we write this FA000, and then the last address we would know that, and it will be adding another 1111 here for in the first 12 bits from the LSB side, and this remains the same. So this is the starting address of the RAM, this is the ending address of the RAM, this is the starting address of the ROM and ending. So how to make a chip select? So you just have to see what is this function. Okay, this is 000 and 1111. So this is the function. So we just have to implement that, right? So it is if you see this is implemented here like this. Okay, so one 3 input AND is taken and another NAND is taken, and these are 000. You have put a bubble out here, right? And here it could be an OR gate. Instead of that OR gate, you have put an inverter in on both the sides. So this has become a NAND gate and prefixed by an inverter. So this function is implemented it like this. Okay. Can you see this? So this is not a unique way of doing it. If it's asked in the exam, you can do your own gates. Not necessarily you need to implement it the way it is done out here, and you can use it the way you want. Only thing is this function has to be implemented to select this chip, right? And here now for the RAM, this is the function which needs to be implemented. So this is this is just a simplest way of doing it and showing it. Just an AND gate is shown here. Okay, so and then a NAND is shown here, in fact, because we want an active low signal. So is this clear how these two circuits have been shown?
Yes, sir.
Yeah. Okay, so this is a simple thing to do. Okay. Now we can also do it using decoders. Okay, so generally we can use 74138. Okay, this is an it is known as an decoder demultiplexer. Okay, where ABC is the input. So if you have 000 input to this chip, you will have these are all active low output. So generally all of them will be high. These are the active low outputs. Okay, starting from Y0 to Y6. Okay, so although this pin is shown here on the left hand side, it is an 16 pin IC. Okay, there on the you will see 1 to 8 pins, and then the rest of the pins out here. So this 9th pin is available here. Okay, not here. Okay, it is just a representation. A is also here. Pin number 1 is here, available here, right? And if you see, when you see an IC, there will be a notch out here. So when you look from top, okay, this is notch is to be kept on the left hand side. So the pin starts here 1. So this is how you identify a chip. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so these 3 pins are the input. So if you give 0, 0, 0 here, right, Y0 will go low, because this is an active low chip. Okay, and if you give 0, 0, 1, A is the MSB, 0, 0, 1, and Y1 will go 0, right? We learnt about decoders, right? So one of the lines, so this is 3 inputs, so 2 to the power of 3. So there are 8 different outputs starting from Y0 to Y7. Y7 is out here. So this pin number 16 is VCC and this is ground. So you have 8 outputs. So one of them will go low based on what is the input which is given here. Okay. Now this also has got 3 enable pins. Okay. So this has to be put to 0, this has to be put to be 0, and this has to be put to 1 to enable this chip. Okay, so if I show you the internal circuit diagram, so it will be like this. These are all the NAND gates. There is a bubble in end, because that is why it becomes an active low. So this is like 0, 0, 0. So this particular since it is an inverter, so in this particular the first NAND has got all A0, A, B and C inverted outputs. So that is why this particular AND gate will get activated for 0, 0, 0. Also for all of these AND gates, you have G1 an inverted output needs to be given here for G1, like G1 requires to be grounded, and G2 and G2A and G2B requires to be given 0. Right, this has to be given 1 out here. No, suppose, yeah, G1 has to be given 1 here, 1, 0, and there is a bubble again out here. So you have to give an plus 5 volt to G1 and ground signals to G2 and B2 for these AND gates to be enabled. So you might be wondering, instead of one enable signal, why is that? We are asking, this has got a provision for 3 enable gates, right? So one should suffice. Why is the requirement of 3 inputs? Okay, so the reason is pretty simple. Okay, I'll explain you. I put one more slide there. In the next slide, I will explain you that. Okay, so this is the truth table. Like if all the like ABC, if it is all zeros out here, then the output will be 0. O0 will be 0, and if it is 0 0 1, now O1 will be 0, and if it is 1 0 0, this will be 0, and so on and so forth. So for these 8 different combinations, one of these lines will go 0, right? Okay, so this is the LSB and this is the MSB. So and here this is the MSB, and the condition required for all these to work properly is G1 requires to be 1, and G2 A and B requires to be 0. Both requires to be 0. So if that is not the case, if G1 is 0, then everything will be 1, or if either of G2 or G1 is also 1, then also the output will be 1. So the reason why we have 3 enables is it helps us in configuring the same chip for a higher bit of demultiplexing. Okay, for example, out here I can use these chips to make it as an 5 into 32 decoder also. So I give these 3 input lines, the LSBs to all the 3 chips. Okay, and the MSB I can give it like this. Okay, into the 2 enable pins also through this inverter, and by connecting the appropriate signals out here. So if you see, if A3 is 0 and A4 is 0, in that case, okay, this chip will be selected because there is a bubble out here. So this chip will be selected for the G1 pin, you need to connect it to the high. Right, so there are 3 enable pins, right? So G1 you are going to connect high, and this is GA and GB, right? G2, these are the left hand sides are G1 and G2, and this is the third one is the G1 out here, right? So although it is written 1 2 3 like this here, so this chip will get enabled. So for 0 1, this chip will get enabled. For 1 0, this is going to get selected. And for 1 1, this is going to get selected, right? So so using an 3 into 8 multiplexer, and because of the multiple enable pins what we have, since we have 2 enable pins, we can also configure this for operation of 3 into 32 decoder. Okay, we can also use 2 chips and make it for 4 into 16 decoder also. Okay, so this is the maximum which we can do, because there are 2 additional pins given out here. So the maximum what we can do is 5 into 32. So this is the advantage of having more than 1 enable pins. Okay, is this understood?
So here for each 74138 chip, we are giving an AND gate as an input to the enable. Is there an AND gate out there?
Yeah. This
okay.
This AND gate is internal. We are not giving it an external.
But it is an AND gate implementation, right?
Yeah. If you see, this is internally available. This whole thing is available internally itself into the chip. These pins are available. So if we give the appropriate signals to these pins, so we can configure it for in this manner, to generate an 5-bit input and 32-bit output.
If we go to the previous slide,
Okay.
in the SEM 138, in the chip itself, there are three separate pins, or G1, G2A, G2B.
Yeah.
But in the next slide that you've given,
Yeah.
there's only one enable input, and the enable input is
No. This is also part of inside.
It's
There are
internal.
three different pins available here.
But what is the exact benefit of keeping? I mean, you mentioned that we can do a 5x32 decoder, but
Yeah.
why do we 5x32 decoder?
No, for there could be different applications, right? Not necessarily we require always an 3x8 decoder. There will be occasions where you will require an 5 into even we'll see in memory location also we might use like for example, let's go to our previous example here, right? So if you want to implement this circuit, okay, with an decoder, this is the function, right? This is now this function has got more than this has got in fact 3, 3, 6, 7 inputs, right? So if you have to use a decoder, right, even this will not be good enough. You will have to have a bigger decoder again, right?
Yes, understood.
This is another example of we need to design an 1K RAM. Okay, so this is the starting address. Okay, so the starting address is given FFC00. So FFC000. Now for 1K, we know that 10 lines are required. So 0 to 9. So we're going to put 1 here. So this has got now. This is going to give me the chip select signal. So I need to implement it with an 74138, right? So how to do that? So this 1 so I put I can pick up these 3 ones out here, the most significant 3 bits, put an AND gate and give to G1, right? Whereas these are all 1s, so where these are active low signals. So I can another 4. How many are left out here? We have picked up 3 out here, and then we need to give we can use these ABC also. We need to give the inputs, right? So we have got another 3 inputs, so that also we can give as for A10, A11 and A12. Okay, and then we can use 2 more AND gates out here, NAND gates out here. So if you see when all are 1 out here, so these will be enabled here, and all are 1 out here, the signal will go low at Y7, right? So now the Y7 has been picked up out here, right? So this is not again very unique design. You can always change the design out here, right? Not necessarily you put NAND gates like this. Ultimately, for all ones out here, your aim should be that G1 should be 1 here, right? And then this should be low here, this should be low here, and whatever input you give here, you need to pick up Y7 and you have, because it is all ones out here, so we have to pick up the output from the most significant output, most significant bit output, that is Y7 out here. So is this clear to all of you?
So this combination will ensure that if A10 to A19 is 1, then only we'll get active low to chip signal.
Yeah. Right? This will ensure that only when all are 1, this particular chip will be selected. Okay, that is known as address decoding.
And we can have different types of ways to give it, right?
Yeah, this is not unique. You could have a different way out to implement it. Okay, there is no standard way to do it, so they could be different ways to it. Only you just have to ensure that this is that the chip select goes low. You have to remember that it has to go low when you all have you have ones out here from A10 to A19. Okay, so let's take one more example out here. in this we say we need to connect an 64K RAM and 64K ROM also. Okay, so we need to generate that. Okay, so so example, we have started off with this. Okay, again this also we can fix it, not necessarily. Okay, for firstly for 64 we are starting with 0000 out here. Okay, and till A15, so 16 bits are required for 64K. So we have taken 00 here and we have put all ones out here. So this range is going to give me 64. Now and then again I have taken 000 here and I have put 111 out here. So this is going to be another 64. Now these two and these two, they just have to be different. Okay, so either you put all zeros out here and you put all ones out here, or you can take anything for that matter. Only thing is these two and these two have to be different. Okay, these two have to be the same. Obviously these two have to be same, but this pair and this pair, they have to be they just have to be unique. Okay, so it could be anything. So accordingly, we can design a circuit. Okay, if it is not specified by the software engineer, and hardware engineer will put something which is out here, which is unique, and implement it, and will tell the software, okay, Bhaiya, this is the memory locations which is available you for the RAM and ROM accordingly, right? So in this example, it has been taken 11 and 00, 11 and 00 out here, right? So now what you do? You got to select the RAM if it is 1100, right? 1100. So how is it done? So you take that particular one, okay, the most significant one, to enable this decoder. Okay, so you have put, now remaining with the 3 bits you have given as ABC. So 100 is 4. So you take an Y-4 and you give it to the ROM, and then okay, and for the next one, for the ROM, this one has already been given here, right? And then 0001, it is 001. 001 is going to be Y1, right? So it is going here. I think it is, this is written other way around, right? RAM should be 100. Yeah, and this is an Y1 and Y4. So this RAM and ROM should be swapped out here, right? And then if you see this also, when you draw a circuit in your exam, well, you got to be careful. You need to specify the address lines which are going to be there for these RAMs. In this case, it is 0 to A15, and this is going to be the chip selector. Now, is this implementation clear to all of you? So pretty simple.
Yes, sir.
Yeah. Okay. So don't get bogged down seeing where did this 11 come from, and it should have been 00, or it should have been, and so don't get when you see the PDF later on, don't get worried that where did this information come from. This is nothing, you can select yourself, whatever information you want, right? So even in exam, if it's given in this manner to implement, you can select whatever data you want, okay, and then accordingly take the outputs from whichever pins you want. Okay, so so that's all for today. In the next class, we will take on how to make and memory, how to connect a memory into 8088. So the only difference in 8088 from 86 is it's only an 8-bit memory. So so it is direct, like it's not an 16-bit. You don't have an even and odd band. So it will be further easy for you to understand. So we will take on 8088 first, and then in the next class we will take 8086. Okay. So that's all for today. If you have any doubts, you can ask me, or we'll call it off for today. Okay, thanks a lot.